In this video, we're going to talk about how do neurons generate signals and how do they conduct the signals. So when a neuron is not conducting a signal, it's at rest, and it has a resting membrane potential. It simply means there's a difference in charge inside and outside the cell, or we say that the membrane is polarized due to the distribution of ions. In the case of a neuron, it's more negative outside than it is more negative inside than it is outside. The resting membrane potential of a neuron is negative 70 millivolts, and it's maintained by a type of active transport called the sodium-potassium pump, which runs 24/7, all day, every day, from the time your nervous system functions until the time the person passes away. So, in order for a cell or a neuron to generate what's called an action potential or a signal, it has to have a strong enough stimulus in order to activate the cell. And so many times it's not a single stimulus that is going to activate the cell, but several stimuli together. So we have what we call local potential changes that occur in the cell, and they're caused by various stimuli, temperature, light, pressure, etc. When the environment changes either inside or outside the cell, it affects the membrane potential by opening gated ion channels, which will allow ions to flow through. If the membrane potential becomes more negative, we say that membranes become hyperpolarized and it's less likely to produce an action potential. If the membrane potential becomes less negative, we say it's depolarized. Like I said, oftentimes it's not a single potential or single signal, but many. So we have what we call graded response, which can be varying strengths, I guess is the best way to say that. So oftentimes, like I said, several potentials have to add up together to create or to reach the threshold. We call that summation. Once the threshold is released, then you can have an action potential. So here in the diagram, you can see at rest, the membrane is polarized, more negative inside than outside. Once we reach the threshold, the sodium channel is open, sodium rushes in, and the membrane goes from negative 70 up to positive 30, where it becomes depolarized. And then the sodium channels close, and the potassium is pumped out, and the membrane repolarizes and goes back down to minus 70. And actually, it goes down a little below that. We have a little hyperpolarization phase, and then it returns back to the resting potential. So here you can see a graph of what an action potential looks like. And again, you can see the changes that go on in that action potential. Like with a muscle, there's a latent period, a period of time after the neuron is stimulated before you see a response. So neurons, like muscles, work through an all or none response. If the neuron responds at all, it responds completely. There's no big or small action potentials, just like there's no big or small contractions within an individual muscle fiber. So a nerve impulse is conducted whenever the stimulus of threshold intensity or above is applied to the axon. All impulses carried on an axon of the same strength. So after an action potential is formed, there's a period of time when the neuron won't respond. We call that the refractory period. There's an absolute refractory period where no matter what you do, there's not going to be another action potential. And then there's a relative refractory period when it would take a stronger than normal stimulus to create a new action potential.